Over the next several weeks, we're going to be looking at functions, equations, and expressions with fractions in them. We call a fraction, technically, a rational number. Well, because we're going to be using algebra, we're going to be talking about rational expressions, rational functions, and rational equations. More specifically, a rational function is a function that can be defined as the ratio of two polynomial functions where the denominator is not equal to 0. Because remember, with fractions, we cannot have a 0 denominator. So here's an example of a function where you would have a numerator that is a polynomial function and a denominator that is a polynomial function. So a little reminder, a polynomial function is going to have variables that only have whole number exponents. So they can have exponents of 0, 1, 2, 3, etc. Whole numbers. They cannot have negative exponents, so a variable cannot have a negative exponent in the polynomial function. They also, therefore, it can't have fractional exponents, and therefore you can't have roots, and you can't have absolute values in these functions. Three examples of rational functions I have listed here. F of x equals 1 over x plus 3. You see the fraction, and the variable there is raised to the first power. Here's another example. G of x equals x plus 7 all over the x squared minus 4x minus 5. Again, when you look at any of these variable terms, the variable is raised to a whole number power. And then h of x, a third example, 3x over x to the fourth plus 5. Again, each variable that you see within the numerator denominator is raised to a whole number power. You'll notice that in addition to variable terms, you have constant terms. A constant term, technically, like 2, the number 2, actually can be thought of as multiplied by x raised to a 0 power, because x to the 0 is just 1, so that's equal to 2 by itself. So if you were wondering, well, where does an exponent of 0 come in? It comes into play anytime you see a constant term like the 7 here or the negative 5. Technically, there's an invisible variable there, but we usually don't write the x to the 0. Now, these functions are fractions, and as such, most of them are going to have restricted domains because denominators in fractions cannot be 0. And remember, we only want to work with real values in our functions, and therefore we need to make sure our domain is going to result in a range that has real number values as well. So one of the things we're going to be very interested in any rational function is looking at and describing its domain, because we do have these exceptions we're going to have to worry about. So let's look at the domain of each of these functions that we have listed here. We'll start with f of x equals 1 over x plus 3. When we look at this, what we are concerned with is we cannot have the denominator equal to 0. This is a no-no. No, basically. We do not want that to be equal to 0, so we want to exclude any value for x that would make that happen. So what we're going to do is solve, so subtract the 3 from both sides, and determine that we cannot have a negative 3 in the domain. So we're going to exclude that. The domain is going to be all real numbers except negative 3. So we could say the set of x such that x is not equal to negative 3. So that would be a way to write that out very simply in set builder notation. If you wanted to show an interval notation, you would go from negative infinity to negative 3 and pop out the negative 3 by using a parenthesis. So that would be how you would represent the domain either in set builder notation or in interval notation. The second function we have listed here, g of x is equal to x plus 7 over x squared minus 4x minus 5, has a more complicated denominator. It's got a trinomial in the denominator. So when we go to think about where that might be 0, we're going to have to factor to solve and use the zero product principle. So x minus 5 times x plus 1 would be the factorization of x squared minus 4x minus 5. We can set each factor equal to 0 and solve, and find out that we have to make sure x is not 5, and we need to make sure x is not negative 1. Those are two values we must exclude from the domain. So the domain of G is going to include all real numbers except 5 and -1. We can write that one of two ways. We can say the set of x such that x is not equal to -1 as well as not equal to 5. So we can just put a comma in between them. Or if we wanted to write that in interval notation, we would say -infinity. And the first number, when you're reading the number line from left to right that will come up of these two, would be -1. So we pop -1 out first because it's further to the left, and then go from -1 to the next number we have to pop out, and then union finally from 5 to infinity. So when you exclude two numbers from a number line, you end up breaking the number line into three pieces. So two ways of writing the domain for G. Now I ran out of room here, so I'll come up here to look at H. When we look at H as denominator, we have x to the fourth plus 5. When we think about that being equal to 0, if you really think through that scenario, x to the fourth, that fourth degree, is going to take any number and take it to a fourth power, so any negative number is going to be eliminated. A negative raised to the fourth power is always going to be positive. If you took a positive and raised it to the fourth power, it would be positive. 0 raised to the fourth power will be 0. When you take a positive number and you add it to 5, you will always get a positive number. You'll never get 0. So the denominator here will never be 0. So what's happening is that it doesn't matter what x value you use in H. It will always work because your denominator will always be positive. So the domain in H is going to be all real numbers. Let's take a look at those same three functions in Desmos and determine through the graph that we do have those domains. Our first function was f of x equals 1 divided by x plus 3. So we see it there in purple. Now on the edges of the graph, you see that the graph seems to be approaching the x-axis, both on the right and the left. In the middle here, you see the graph going either sky high up here, or you see it going really low down here. If you look closely at where that happens to be, that's occurring at x equals -3. If I type in x equals -3 here, you can see that happening. This line at x equals 3 that the graph doesn't touch but gets really close to is what we call a vertical asymptote. And typically a vertical asymptote, when you show it on a graph, will be dashed. So I'm going to take that style button, click and hold, and then make that a dashed line. In fact, I'm going to make it green just so it stands out more. So the function graph is the purple graph we see here. The vertical asymptote at x equals -3 is not part of the function itself. It is a relationship the function has, that it gets really close to this graph of x equals -3, but it doesn't exist at x equals -3. It's not technically part of the graph. It's a relationship that it has when you look at its graph. Now, let's look at the second example, but we can definitely see that -3 is not part of this graph. It is separate. The graph approaches it instead of being on it. Let's look at the other examples we had. We had g of x equals x plus 7. Now, if I just say divided by here, it's only going to divide the 7. So instead, what I'm going to do is before I say divided by, I'm going to highlight all of x plus 7, then divide so that I have x squared plus 7 entirely in the numerator. My denominator is x squared minus 4x minus 5. So here's my new function of g, graphed in red in this example. And when you look at the graph, once again, it's approaching, as you go to the left and the right, it looks like it's approaching the x-axis. But where you have in the middle of these places where the graph goes sky high, so y value is going to infinity or -infinity. And if you look closely, that's going to be in one case where x equals -1. So the graph does not exist at x equals -1. It approaches the graph of x equals -1. So it's approaching the number but not actually getting there. Again, we call that a vertical asymptote. The graph has an asymptote at x equals -1. The other place this happens is at x equals 5. I'll draw that one in as well. making it dashed so that we, as we do for asymptotes, we can see once again the graph is approaching that line, but it actually doesn't reach it. So we have two domain restrictions on this graph. The graph doesn't exist at -1 and it doesn't exist at 5. The third example, remember we thought it had a domain of all real numbers. Let's go ahead and graph that and see if we were correct. So h of x is equal to 3x divided by x to the 4th plus 5. Oops, my plus 5 ended up not in the denominator, so let me change that. Plus 5, there we go. And what you see here when we look at this graph is it does get really close to the x-axis on both ends, but it doesn't have any asymptotes, vertical asymptotes. There's no place where the graph doesn't exist. If we look both left and right, it's going to be continuous everywhere. There's no place where the graph breaks up and is not continuous. So this does have a domain of all real numbers. As we look left to right, the graph continues to exist. As we mentioned, rational functions often have asymptotic behavior in their graphs. Their graphs will often approach or get very close to either vertical or horizontal lines. I'm going to have us identify the vertical asymptotes in these functions down below, as well as the domain and range. So when we look at the vertical asymptote of these functions, we have a vertical line right here at x equals, well, this is 10, -10, this is 0, so that would be x equals -3. So we have a vertical asymptote there. The vertical asymptote is a line that the graph doesn't cross, so that's an x exception. So our domain would be all real numbers except -3. So we would say the set of x such that x is not equal to -3. And then the range, if we look closely in terms of y values, notice the graph seems to be approaching this value right here, this y value of y equals 2. So, and because it's approaching it, not crossing it, I've actually labeled it as a asymptote there. So the y values would include all values except +2, because we also have a horizontal asymptote where the line doesn't cross. In the next example, we have two vertical asymptotes shown off by these dashed lines, one at x equals -5 and the other at x equals 1. So these are vertical asymptotes. Remember, the vertical asymptote are places where the graph doesn't exist. You'll notice the graph goes sky high toward it without ever touching it, and then down below without touching it. So the domain would include all values except those two. So the set of x such that x is not equal to -5 or 1. The range here would be all y values that are possible. Now it does look like the graph is approaching the x-axis, so it might have a horizontal asymptote out here on the edges approaching the x-axis, but in the center it does go through the x-axis, so it is possible to be on the axis. In fact, if we look at the middle portion, we appear to have all real numbers for y values. The graph goes all the way up and all the way down with no breaks in between. So the set of all y would be all real numbers.